I'd like to start by reiterating what a few people have said. I was a volunteer on this exhibit project, and I just want to say the staff at the Computer History Museum and Kirsten and Dag and their people are really fantastic. So I really appreciate what they did and the exhibit that they mounted. I also want to say that looking at this audience is scary. I mean, this is like, among the best people who ever practiced computer science and computer technology are sitting here in this audience. So it is a humbling experience to be talking to this audience. And the third thing I wanted to say in prelude was that in contrast to David and some of the others on this panel, I am not a chess maven at all. I've been following the history of chess-playing machines casually as an AI scientist, and I'd like to address my remarks tonight as an AI scientist, but don't ask me any questions about chess. The first comment, I just want to make three comments in my short remark. The first is that I was around, and Monty has promised to ask me questions about this, at Carnegie Mellon University, which was then, incidentally, Carnegie Institute of Technology. When Newell and Simon and their colleague at Rand Corporation, Cliff Shaw, decided to pick chess as one of the domains of work in which they were going to explore new ideas in thinking machines. It wasn't the only one. They started out with proving theorems in propositional calculus, and they did other things as well. But chess was a major focus. And they did it because they thought that it was a route that would lead them to understand human problem solving better, because it was thought to be a extremely challenging problem for human problem solvers. And they weren't the first who thought that. Of course, we know that Turing wrote about this in the late 40s, early 50s, but he also talked to others in Britain about this earlier, and he himself thought that, and so did Shannon. Shannon wasn't mentioned in the rundown of people, but he was important in all of this, and other people at Los Alamos worked on this effort. So these people were great visionaries, and they took the problem of chess playing seriously, and I think that it's really worthy of our attention, and it's worthy of the first of these great exhibitions at the Computer History Museum. They were wrong on the time scale. 57, Simon gave a talk in which he predicted that a machine would beat the world's chess champion in 10 years, and he was wrong by 30. It was a 40-year history, not a 10-year history, but that's the way it is with AI. And we're really happy. The problem is that this feat was achieved by a technique that we all thought was basically impossible. So it serves as what you might, if you're one kind of scientist, you would think of it as an outlier point in the space of achievements of artificial intelligence. If you're another kind of scientist, you'd say it's really a challenge to the fundamental hypothesis that AI has been living with, growing up with over the last 50 years. It's about to celebrate its 50th birthday. And that is, let me try to sketch that by starting at the bottom. Problem solving is viewed by AI scientists as search in a maze. The mazes are enormous. Some people have, not me, I haven't checked this myself, but some people have estimated that the size of the chess maze is 10 to the 120th pass. And that's relatively small compared to what you might call real world problems. So the size of the problem space, those are called problem spaces, is enormous. And that any kind of what you might call brute force search, although it ended up in the famous chess playing programs of being not totally brute force, but that brute force search was fruitless. That you couldn't, no conceivable computer could search out the solutions to problems in the time remaining in the universe, or even store intermediate results in all the matter that existed in the universe. So, of course, we invented another way, and that was the use of knowledge. That wasn't an that wasn't an invention that came later, because, I mean, I was there at Carnegie Tech when Herb Simon, Al Newell was doing one hell of a lot of programming with Cliff Shaw at the other end of the teletype line at the Rand Corporation. But Herb Simon was reading lots of chess books. I mean, he was really becoming, he never became a David Levy in terms of quality of chess play, but he really got to know chess very well. And Alex Bernstein, who worked at IBM, was himself an expert at chess. So the idea of applying knowledge to the chess problem space was not a new idea. And it became the standard idea in artificial intelligence. These experiments that Monty was referring to before with the Dendral program for hypothesizing organic molecules from mass spectral data, we actually ran what you might call titration experiments, in which we ran search versus knowledge. We kept titrating in more and more knowledge of chemistry and watching the search be reduced and watching the quality of the problem solutions improve. And we published all of that. So AI people began to talk about what's called the knowledge versus search spectrum. And almost all the points on the knowledge search spectrum ended up on the knowledge side, not on the search side. So it was really remarkable when in the 90s, the developments that you've heard of began to produce world-class problem solvers in a problem that the early and great visionaries that I referred to early on in my remarks had thought was such a quintessential, wonderful problem. You apply factors of, let's say, 10 to the 7th more computation than you had before. Why that has any impact on a problem space that's 10 to the 120th big? What's 10 to the 7th? That's nothing. You'd think that knowledge would win. But, and also people process information very slowly, and they are extremely good chess players, even though computer programs now beat them. Anyway, I think that we still have a lot to learn from chess playing as a domain of inquiry. We have now, when I said one data point, I meant chess playing, but actually that's a mistake. There are dozens, hundreds of these different chess playing programs that we need to analyze carefully from the point of view of knowledge versus search, and try to understand why the search strategy paid off. Okay, final comment. It has to do with combinatorics and creativity. I've been over this territory numerous times with my former colleagues working on the Dendral project, Joshua Lederberg, Nobel Prize winner in medicine who collaborated on the Dendral project, and Bruce Buchanan. The Dendral project was one of these vast combinatorial, the Dendral problem solver was faced with one of these vast combinatorial problem spaces, and it used knowledge in organic chemistry and mass spectrometry and NMR spectroscopy to narrow that problem space to home in on correct answers. And so we've discussed often the question of what could lurk in those problem spaces. Could there lurk some unique or very surprising, quote, creative, unquote, solution to some problem? After all, the problem space is so vast that you can't see it. So as you search, if you have the right heuristics, will you come upon some really creative solution to some problem? And is that really the answer to what is creativity? In 1956, when Newell and Simon first started to prove theorems in Whitehead and Russell, there was one theorem in chapter 2, which was a a longish theorem. It took about 2 pages for Whitehead and Russell to prove, and I think that the logic theorists proved it in something like 2 or 3 lines. And Simon wrote this up and sent a letter to Bertrand Russell. It's all discussed in Simon's autobiography. But you might say, how was it possible for a program in 1956 on those primitive early machines of 4K memory or 8K memory to come up with anything, quote, creative, unquote, like that? It was just finding it in a space. So with that in mind, I was very much struck by the remarks that Kasparov made, both written and interview remarks after the game that he lost, where he talked, I don't have the quotes in mind exactly, but there was one, Kirsten could quote them accurately. One, he talked about something like he got into this, he thought he was looking into the mind of God. And, that's not literally true, but he was spooked. And he even said he was spooked. He said that there was a move in one of the games that really got him jittery, and well, David, you can tell the story better than I can. But anyway, what's that all about? What that's all about is these huge combinatorial spaces. And humans can see so little of it. And there are numerous avenues in those spaces where you can find something truly novel, truly surprising. And that's what we call creative.
Thanks very much.